called Iris Tube Technology by Dr. Marty Ravenhorst. Today's webinar is going to be recorded, so that'll be available after the webinar online at soils.usda.gov/education/resources/videos, and that'll be available for viewing within the agency and outside the agency, of course. Today's presentation, everyone's in listen-only mode except for the presenters. You can submit a question using your live meeting Q&A tab at the top of the live meeting frame, and at the end of the presentation, we'll have a chance to answer those questions, and our presenter will respond to those. So with that, I'm going to turn it over to our presenter, Dr. Ravenhorst.
Good afternoon, everybody. Take a minute to start by thanking Sean and the folks at the Soil Survey Lab for inviting me to participate today. Thank you for signing in and being on the webinar. So I don't know how things are where most of you folks are, but we got a pretty raw, rainy, cold winter day, and I felt this a little bit bad, so it's like we could ravage students out in the field today alone. Anyway, this might be a good day to be indoors at a webinar rather than out in the field. So we're going to talk about the iris tubes and what they are and how to use them. And I imagine different ones of you have got different levels of experience with iris tubes. We'll start at the beginning and work our way all the way. And here's the outline of what we're going to be doing over the next hour or so. Start with just a brief discussion of sort of the underlying theory. We put off, I hope, too much by the redox chemistry, but it's just helpful if you're going to use the method to understand why it works, how it works, and why it works. I'm going to say a little bit about making iris tubes. Most of you probably aren't in the situation where you'll be making them, you'll be more apt to be using them, but some of you are involved in making them. Whether you're using them or making them, it's helpful to kind of understand what goes into it, what to look for to make sure you're ending up with a product or using a product that's functional or optimal. And we'll get into sort of the guts of what most of you may be interested in. Deploying, monitoring, how do we install them, what are our monitoring strategies, and how do we document the data which are collected on the tubes, how we interpret that. And at the very end, I'm just going to say a couple of things about some other applications of iris tubes. I've really been working with this since about 2005, and I ought to start just by saying that Byron Jenkinson, who is actually the originator of the iris tube, his doctoral dissertation at Purdue University, working out the sort of the basics of the methodology. And then we picked it up and we've used it a lot, further developed it. But we should certainly recognize Byron for his contribution. So let's begin with a little bit of the theory. Iris tubes, as the acronym says, indicator of reduction in soil. So we're interested in reduction, soil reduction. And soil reduction is tied very closely to saturation. You can't get soil reduction if you don't have saturation in the soil, so that's the starting point. As the soils become saturated through ponding or through groundwater, the pores get filled with water rather than air, it really slows down the diffusion of oxygen into the soil. So oxygen then has to be depleted if we're going to develop reduction. And the mechanism by which the oxygen is depleted is you've got microorganisms in the soil, they're using organic matter, and as they're oxidizing the organic matter, they're reducing something, and that something oxygen. So as the organisms are active, then the oxygen becomes depleted. So if that's the case, you're going to get that kind of depletion of oxygen. You also have to have the presence of microbes. Microbes are essentially ubiquitous in soils. You've always got the right bugs and everything else. You've got to have some kind of an oxidizable source of carbon. Usually it's plant organic material. And it's got to be warm enough for the microbes to be active. That varies a lot from place to place. And microorganisms tend to adapt. Dr. Chin Lu Ping up in Alaska will tell you that they can get reduction of soils even when they're frozen. Most of the world, thermomagnetic temperature type regimes, when temperatures begin to get cold in the winter, as temperatures get down close to 4 or 5 degrees C, the microorganisms really slow down their activity. Anyway, if you can have saturation, but if you don't develop anaerobic conditions, you have what we all know as oxyactive, saturated but still oxidized. For certain applications, that's problematic. You don't really care about the reduction. If you're interested in home sites and basements, you don't really care if the water's coming in, whether it's anaerobic water or aerobic water. If it's coming into your basement, it's a problem. Whereas in the case of wetland function, a lot of it's tied to this anaerobic condition. There are certain particular chemical reactions that go on in wetland anaerobic conditions. So that's what we're all about. Now, as the carbon is decomposed, it starts first to consume oxygen. And oxygen is the electron acceptor, and it gets reduced to the oxygen to the compound water. So the reduction is a loss of electrons, and so we end up with, first a gain in electrons, so we end up with this reduction of oxygen, elemental oxygen, water. But once the oxygen becomes depleted, other microorganisms become involved, and they start using alternate electron acceptors other than oxygen. Next one in line, if it's present, is nitrate. And nitrate it can get reduced to nitrite. Eventually, it can get reduced all the way to nitrogen gas, which is referred to as denitrification. Farmers hate it, and people concerned about eutrophication love it. But it's an important reaction. But most soils really don't contain very much nitrate. Nitrate's usually present pretty at low levels. That's why cultural systems seem to add a lot of nitrate. So when nitrogen gets depleted, the next thing down this redox run, we're sort of walking our way down this ladder from oxygen down to nitrate. The next one down is manganese oxide. Manganese +4 forms black manganese oxide coatings, either as nodules or as coatings in soils. And manganese 4, or manganese oxides, can be reduced to manganese 2, which of course makes also very soluble and colorless. And this leads to the dissolution, actually formation of manganese features. But there's not usually a whole lot of manganese in the soils either. There's usually more than nitrate. But the next rung down the ladder below manganese is iron. And relatively speaking, there's a lot of iron oxide in soils. Most well-drained soils are looking at anywhere, reasonably well-developed soils, somewhere between 1 and maybe 4 or 5% iron oxide. There's exceptions with higher or lower than that. Iron +3, these iron oxides, can be reduced to iron 2, which is the iron oxides. You're familiar with goethite, hematite, these things that make soils red and brown and orange. When they reduce, they become insoluble, or they become colorless solution. They're highly soluble, but they're colorless. And we're going to come back and spend more time on this. But sometimes these ferrous iron compounds can cause the present silicate minerals can cause them to become blue or green. But you might read wrongly in some literature that ferrous iron in solution is blue-green. It's not. Colorless. And I put a box around here because this is one of the major reactions that's involved in iris tubes. So we're going to come back and talk about the implications of this. Beyond iron, if it gets more reducing than the reduction of iron oxide, you can actually reduce sulfate, if there's any sulfate present, to sulfide. This is most commonly occurring in estuarine coastal type systems where you got to have enough salt. You might also have it in some be potholes or some drier parts of the country where you might have higher sulfate levels. Most of the humid part of the world, sulfate's pretty low. Not present very much less than type C. But if you do form sulfides, if there's any iron that's present, you can actually form some black iron sulfide compound. Either this iron monosulfide, FES, which is a very black pigment. And we'll come back and actually talk a little bit more about that. Or in extreme cases, given enough time, the monosulfides will convert over here to pyrite. So that's not a big part of the story, but we're going to touch on a little bit later on. And then wetlands under the extreme conditions, especially if there isn't any sulfate present, can have the formation of methane. Big deal in wetlands, serious greenhouse gas. So that's the extent of that. So let's, if we take a look at this, this represents this redox ladder we just were going through. Maybe some of you have seen this is a pH diagram. The important thing is it gets more reducing as you come down the pH axis. So we start up here with aerobic conditions, we reduce nitrate, manganese, and then we get into this zone with the iron oxides. The two dominant iron oxides of concern in soils, although are ferrihydrite, goethite, and hematite is pretty similar to goethite in terms of where it occurs in the diagram. And so this is where we're going to spend most of the rest of the time. This reduction of iron oxides is really what drives a lot of soil hydromorphology. The iron oxides form these natural coatings. As you know, soils are red, yellow, brown colors. They become reduced under anaerobic wet conditions. You can get mobilization, stripping, where you expose uncoated mineral grains, silt, sand, quartz, feldspar, clays. They are gray in color, and so you get these redox depletions. Sometimes deeper in the soil, sometimes closer to the surface. We actually end up with the hydric soil. So, very briefly now, I'm going to give you a quick overview of iris tubes, how we're talking about. So what we start with, if we're going to use iris tubes, usually we begin by putting in a pilot hole of some sort, push probe. Each pilot hole is going to receive one iris tube. Then we go ahead and proceed to insert the iris tube into the pilot hole. Either the soil at that point over time becomes anaerobic, sometimes it's anaerobic when the iris tubes go in. And during that time, the microbes are oxidizing organic materials in the soil. If it's anaerobic, you're going to start looking for other electron acceptors. What we've done in putting the iris tube in is we've added a lot of iron oxide right in this vicinity here. But it's present as a thin coating of iron oxide, as we'll see in a minute. The iron oxides on the tubes become utilized by the microbes as the electron acceptors. You know that iron oxides, when they're oxidized, are the solid orange-brown precipitates. And as we said, when they become reduced, they become colorless, highly soluble. So as this happens, as it's reduced from iron 3 to iron 2, it becomes soluble, and various parts of the iron oxide get stripped off the tubes. Then, where these are apparent, we can come in and we can document them. That's the data that we're going to collect from the iris tubes. So that's the background. I want to say a little bit about making iris tubes. Short version is we put an iron oxide paint on half-inch thick 40 PVC tubing. The tubing, if anyone's involved in making these, so it's preferable to use what we call environmental grade PVC that doesn't come printed with these letters all over. You go to Home Depot or Lowe's like we did at the beginning, you always have this lettering over it. And, we try to get it off with acetone. It never comes off very well. That's a great thing to use. But, again, this is a pretty cheap component, right? You can buy a 10-foot piece of PVC pipe for $1. So if you buy the environmental grade, it's like $2. So it's still a pretty trivial cost, the overall cost of making iris. We then mount the tube once it's prepared. in some kind of a lathe device. And you can see this very sophisticated, fancy, high-tech lathe used, which is a cordless drill. And we just put a little friction fitting, a little rubber stopper in here. And then we use that to rotate the tube so we can get the paint applied evenly. This is our early version. It just has the cordless drill up here. I guess if you're making a few of them, it's not such a big deal. When you're making a lot of issues, you have to figure out some way to kind of hold that trigger at the right speed. So our upgraded version, we took this is a non-cordless drill that we strapped into a bracket, and I put a little tube gasket, tube fitting around here, hose clamp, that we could adjust so we could get the speed the way we wanted. Still pretty modest device, right? Pretty cheap. And it's friction fit over the, I think it's number 1 or number 0 stopper, holds it in place pretty well. So we stick the tube on there. Sometimes you can do your sanding. We do a very light sanding. And I'll say a little more about this in a minute, but we use a very fine sandpaper, like a 200, 300 grit or finer. It's a very light sanding, just enough to kind of take the shine off the tube. Probably not even necessary, but it helps ensure that the surface is clean. You can either do the sanding on the lathe while it's spinning, but you can just as easily do it outside the lathe, just hold the tube and give it a light sanding. It doesn't take much at all, really. Then we put a mark on the tube at 50 centimeters so that we know that will be sort of our markers. We're inserting the tube to a uniform depth. Mark the tube. Then we proceed to apply the paint. So we use a foam brush like this. Actually, it looks pretty simple, but it's fairly involved. And you'll see there's a web address down here at the bottom of this particular slide where I have loaded a video. I used to tell people this was a 20-minute video until I looked a little more carefully and I found out it's actually a 36-minute video. If you're wondering how in the world could you spend 36 minutes on a video how to paint iris tubes, in retrospect, wondering that myself. But actually, I feature one of my graduate students, Phil Heidi, who probably painted 2,000 or 3,000 tubes. He's a real expert, and there's some just little tricks that would be helpful. So if anyone's interested, you can copy down this web address. I'm sure it'll be available for this version as well. And you can sit down to watch this. I suggest you get either a nice cold beer and a relaxing chair or something. It's not a real fast-moving video. I get relaxed and watch it. Once they come off, after they've been painted, you need some kind of a rack to put them in while they dry so they don't bump up against one another until the paint dries. This is about as cheap and easy as you can find, right, with the old test tube rack that we use. We've also created some slightly more sophisticated racks for a larger volume, but not too big a deal. We also built some racks. Actually, one of my former students, Steve Birch, built these racks for taking tubes to the field and back. And these are just some wooden frames. They've got some nails in the bottom that they sit on, down. They come from below. And then these nails at the top walk through drilled holes you can sort of pull in and out so you can slide the tube. Keeps them from bumping against each other, from getting abraded when you're taking them in or bringing them out. But if you're only using a small number of tubes, it's not that big a deal. So let's talk a little bit about quality issues, because I know this is a concern for a number of folks. A lot of the tubes that I've seen have come from various places, sometimes aren't very good quality. And if you don't have a good quality tube, you're going to get frustrated. You're not going to get reliable data. And the biggest problem that exists is that the paint rubs off too easy. You get this kind of a phenomenon while you're handling the tubes. And it's a serious problem, but it's an easy problem to fix. Fix it before you make the tube. You can't fix it after the tube's been painted. But it really boils down to not having the right mineralogical mix in the iris paint. As I mentioned earlier, Byron Jenkinson's the one who invented the iris tube. But I spent a year and a half figuring out how to get the paint to stick. The recipe that Byron had published in his dissertation had some issues with it, and the closer we followed it, the more trouble we had. We ended up with this kind of at the moment. But we did finally get a solution. That's what I'm going to say a little bit about. It has to do with the proportion of goethite and ferrihydrite. This paint, iron oxide paint, is made up of two minerals, goethite and ferrihydrite. And what we found, when you make the paint, it starts out being essentially all ferrihydrite. And then, as it ages under the right conditions, it gradually becomes more goethite rich. What we discovered is this durability index, this is just sort of a relative index. Durability is 5. You can handle a tube with the paint durability of 5, and it's not going to come off in your hands at all. Whereas, 1 is where it just kind of rubs off as soon as you pick it up. So there's a range of scale. But as we kind of tried to quantify this, once you get about 40% goethite in the system, the paint is good, and it'll stick. This is a little bit of a complicated graph, but let me just, the bottom line, there's a time sequence along here, so this has to do with the aging of the paint over time. We started up here with 100% goethite, and especially if you titrate it at a low to middle pH around 7, which is what was originally prescribed, you start out with 100% goethite, and if this is your pH over time, it really doesn't change at all. And if the mineralogy doesn't change, it's not going to end up ever with a good quality paint. We had some of these paints that we kept out 3-4 months, and they still wouldn't work. The solution is you titrate the pH to a higher pH, pH 11 or pH 12, and depending on where you start, it starts out with still mostly ferrihydrite, but over time you can see you've developed more goethite. Go from 100% goethite on this axis down to, or ferrihydrite down to 100% goethite. And this is the magic number, right? 60% ferrihydrite, 40% goethite. Once it gets down to that level, the paint's going to work. Guaranteed. And if you're starting out with stuff that's a pH 12, it might take a week sitting on the lab bench to get down there. Start at pH 11, it might take you several weeks, or months or longer to get out there. It's going to be a lot slower. So we typically make the paint at a pH of about 12. All right. This is illustrating some tubes similar to maybe some that you've gotten. I hope the ones that you got look like these ones on top, which I call good. And these have the right mixture of ferrihydrite and goethite, and I put them together here because you can see they're a little bit yellower than these tubes down here I call bad. Bad meaning it rubs off when you're handling it. These have kind of a shiny luster, kind of a satin to sort of a weak semi-gloss kind of a luster. These down here tend to be a little more dull. Main thing is you can see these are a little more red, and these up here are just a little bit more yellow. That's because the ferrihydrite by itself is sort of a deep red. Goethite tends to be kind of a yellowish brown. So sometimes I can just look at a tube and just by looking at the color, I've seen enough of these, I can say, well, that paint's what I actually do, and while we're, once we sort of create the paint, we're waiting to do this, is that every couple of days, we paint a little bit, just a 2 or 3 inch section on an iris tube, and we let it dry, and then we put our finger on it. See, well, does it rub off? Is it stable? And then a couple of days later, we'll do it again. I'll put the date, I'll label it, and then a couple of days later, I'll do it again and put the date on it. This is a tube I just made up a batch of paint a couple of weeks ago. And between the time we pulled it out and we're starting the lab incubation, it was about 10 days before it went from something that was clearly not good enough, didn't have enough goethite when you get tubes are sent to you, you should be able to handle them just fine. And they should have this kind of an orangey color. It shouldn't be too red. It shouldn't be dull. And it shouldn't rub off easily. Here's an example of 5 tubes ready to go. They should be smooth. Should have kind of a satin or slight gloss finish. It should be durable, meaning not going to rub off with normal handling. However, I do have this caveat point is that it may not be durable under rough handling or firm intentional rubbing. You can take a good tube, and if you really lean into it, you can rub some of it off. It's not like an enamel-based paint going down to the hardware store. I mean, you can really work, if you work at it, you can rub it off. But it shouldn't come off easily. It shouldn't come off with normal handling. It shouldn't come off from just rubbing your finger back and forth on it. Right? If you have paint that comes off, it's not going to behave right. It's going to come off easily. It's going to scratch easily when you're installing the tube. It's going to create all kinds of trouble. So you want to make sure you're starting with good tubes. The other thing I would say is that I know there was a while when some folks were making tubes, they were using a really coarse-grained sandpaper. So the tubes were rough. This is a bad idea. And you really shouldn't use those tubes because it actually interferes with good paint adhesion. And it increases the likelihood you're going to get scraping and blemishes in the paint when you're using the tubes in the field. So this is why we say use, a 220 or 300 grade sandpaper to sandpaper the tubes. You've got some of these tubes that are deeply, they feel rough to the touch. You want to trade those in for better quality. Okay, let's talk about actually using the tubes. Deploying and monitoring the tubes. Typically, we're going to put these in when the water tables are expected to be high, right? If you have a seasonality in your water tables, you want to do it when you expect the water tables to be up because you're not going to get reduction unless you've got saturation. You want to do it when you expect soil or part of the soil to be saturated. And usually at a time when we expect the soil to be warming because this is a microbial activity. There is some temperature effect here. We've shown that. So up here in the mid-Atlantic world, our wet season is related to ET. So usually our water tables start coming up in the late fall, early winter, usually at a maximum by February. And they stay at a maximum until March. So usually, but things start warming up. We get leak out here around April the 1st. So typically we'll put in, tubes in March or April or May, kind of in the spring, while the water tables are up before they get pulled down by UV. To install the tube, you first have to make a pilot hole. And also, I should say, usually we use 5 replicate iris tubes. And that's because redox type processes in soils are fairly variable. There's a lot of variability, microsite variability. And from work that we've done and other people have done, we've shown that there's enough variability that you want to have replication. So you make a pilot hole using a fish probe. You all know these tools. These are not the soil surveyor's tools much anymore, but they're out there for various applications. And you'll notice that the actual dimensions of Schedule 40, half-inch Schedule 40 PVC has an outside diameter of 0.84 inches. Okay, that's just a tad under 7/8 of an inch. So I know AMS makes a probe that's 7/8 inch diameter. That's the one that we usually use. They also make one that's like a 1 1/8 inch diameter probe. You wouldn't want to use that. That would give too much leeway. Standard Oakfield probe, which I've also used, is just a tad smaller than the iris tube, but normally, unless you've got something that's really abrasive, that shouldn't create too much of an issue. We mark the tubes 50 centimeters up from the bottom, because we want to make a pilot hole 50 centimeters long, because that's how far we're going to insert the tubes normally. Once you make the tube, you just slide the iris tube in the hole. And as I said, as I indicated tubes. You have replica tubes. They say within a, spread them out over about a yard or a meter or two, something like that, right? Maybe the size of a pedon, if you're thinking those concepts. So you put in 5 replicate iris tubes. You can use a variety of patterns or randomness, or whatever works for you. It really doesn't matter too much. You just want to spread them out over an area that you think is relatively uniform. This is the zone you're trying to measure document. Sometimes you encounter limiting layers or something that's going to interfere. It could be bedrock, it could be some gravelly zone, coarse fragments, something that's going to interfere. And if that's the case, you just put them in as deeply as you can, then just come back and mark the surface. Because all these measurements, all these evaluations are based on usually some distance or zone from the soil surface. So as long as you know where the soil surface was, you can still use these codes over here just as well, as long as you've marked the soil surface in a way that you know where those are. So here's an example of a set of tubes that's actually 6. I don't want to put 6 instead of 5 in here. But they're installed at 50 centimeters. We mark all of these with a line that they're all in right up to the line. But here's 5 other tubes. As you can see, we weren't able to install all the way to 50 centimeters. There's a gravelly substratum. This is an alluvial setting. There's a gravelly bed down here. And it only allowed us to put the tubes into a shallower depth. And the critical thing is to mark the soil surface. That is, when you pull those out, you know where the surface was relative to the top of the tube. One of the other issues that sometimes gets mentioned is scratching. So I want to say a little bit about that. I put in 3 example tubes. I dug back through my archives, found some tubes that show some evidence of scratching. Normally I'll say that scratching isn't normally much of a problem. And maybe that depends on how good your paint is. In fact, I'm sure it depends. If you've got a poor quality paint, then you're going to be more apt to be subject to scratching. If your paint is of good quality, that's going to be less apt to happen. The other thing is if you've got a particularly abrasive soil or a dry soil, after you make your pilot hole, it's also possible you might want to pour a little water as kind of a lubricant to help prevent scratching. That might help if you're installing it while it's dry, if you're expecting water tables to come up, or in a minute you're using in kind of a reconnaissance mode, in which case you might be installing them before the wet season arrives. You might be able to do that. But the other thing I'll say, and let me highlight this third point, is that normally you can easily differentiate between scratches and paint removal that's driven by these microbial reduction processes. You'll notice that where we see scratches on these tubes, most of my tubes don't have serious scratches on them, but these are a few that I found. They're almost always vertically oriented, meaning that they were induced either when the tube was going in or when the tube was coming out. So by pushing it straight down or pulling it straight up, occasionally you can create some of these scratches. But I guess my point is, these vertical scratches are pretty easily distinguished from these other sort of splotchy pattern zones, whether it's this little one here, these little ones down here, this large zone here. Pretty easy to tell what the scratch is, what is in most cases. Here's a case where this is also, I think, a vertical scratch. It's a little broad with a spear, but this is one I think wasn't painted well. I think this is one of the real early tubes that you sorted out. Now, another issue that's a real issue in terms of abrasion and scratching is the case if you're dealing with saturated sand. You haven't seen this a whole lot, but you've seen it sometimes. Because if you're dealing with sand, I'm not talking about sandy loams or even loamy sands, but really true sands that are saturated, as you know, if you try to auger in these, sometimes they'll start to flow. So if you make a pilot hole, the pilot hole often won't stay open. So you end up, if you force the tube in, you just really are pushing against the grain, not into a pilot hole. And so we end up with some tubes like this where the paint's actually been abraded entirely off. And it's an unusual case. Unfortunately, there aren't too many cases like that. I don't really have a good solution for it. Once they've been in and you're ready to pull them out, extraction, I'll say normally straightforward. Reach down, grab them, and pull them out. You want to pull them straight out. You don't want to twist. Right? Twisting will induce abrasion. Although sometimes they get a little bit stuck, and especially if you're dealing with some fine textured soils. I found sometimes I really had a hard time getting a hold of them, especially if it's a wet out, slips through the fingers. So occasionally you'd use pliers or vice grip where you can grab hold of that tube. Again, you just want to pull it straight out. Occasionally you can rock these just a little bit back and forth. You don't want to twist it, but if you rock it one way and then rock it the other way, then usually you can pull it straight out without using much in the way of scratching or abrasion. Now, usually, I'll call basic monitoring, we put the tubes in for about 4 weeks. My suggestion is that the day you put the tube in, you use a Sharpie permanent marker and write the date on there, and then when you extract it, put the date out. If you're using a waterproof pen, we did receive some tubes in our lab that some people had deployed, and they came in and they still had some soil on them, so we were washing them off. We were very sorry to discover about halfway through the process that they were labeled with water-soluble pens. And so we lost all the identifying characteristics as we were rinsing the soil off the tubes. Well, I'm sure none of you would make that. So when we put them in for 4 weeks. Sometimes we'll put them in a sequence. We'll put them in for 4 weeks, and maybe we'll put them in for another 4 weeks after that. Standard protocol, especially if you're using to document the Hydric Soil technical standard, is to have your tubes in for about 4 weeks. And the reason that we might sometimes have multiple steps is you're not always sure what the hydrology is going to be that year. So, you might put them in March, but March is a cool month. It's going to be warmer in April if the water table stays up, and it's going to be even warmer in May if the water table stays up. So sometimes we just plan on putting in several sets. When we've been doing some research activities, sometimes we've done actually some overlapping at the 4-week period to get a little finer resolution. But, for most cases, that's overkill. You don't really need to do that. So that's sort of your standard approach. But there's another way that iris tubes can be used, which is really helpful, and that's what we call sort of reconnaissance monitoring. There's an area you want to know, maybe are these hydric soils or not? Maybe might they be hydric soils or not, or wetlands? So you can put the tubes in and leave them in for a long period of time, 3 months, 6 months. Actually, you can leave them in for a year if you needed to. If you've got some really remote areas, you're going to be back next year, or next fall, or next spring. You can put the tubes in before you think it's going to be wet, as long as they're in place during the wet season. But then you can install them, and if you don't see any paint removal, then you're pretty clearly sure that that's not a reducing system. It's not hydric soils. You don't need to worry about that. The caveat, though, is if there is paint removal, you can't conclude necessarily that you got wetlands or hydric soils because they've been in there for 6 months, and this paint removal, because it's microbial, is cumulative. The longer you leave them in, more paint's probably going to come on. So, but if you do see significant paint removal, then you can conclude that there might be reduction. There might be a hydric soil there, might be a wetland, in which case it might warrant then further testing. Up here you don't see, you don't need to worry about it. Assuming it's an average rainfall year, right? All about those caveats. So we don't use the reconnaissance approach to document the technical standard. You've got to have those in for a shorter period of time for that. Now, what about measuring the paint removal once it comes out? How do we go about doing that? Well, initially, we started out taking photographs of tubes and rotating it 3 times, and then compositing it together. That was a lot of work. Then we could use some sort of a technique, we'll talk later, image analysis, something to measure the amount of paint that was stripped off those tubes. That's a fair amount of work. What we've done more recently, and I say this is for research purposes. This is not for sort of field. We'll talk about field applications in just a minute. But for research type purposes, if you really want to sort of document carefully the amount of paint that's removed. We built this flatbed scanner. We took a saw to it. Can you believe that? See where we sawed off, sawed open the side. We had to pop the top off of this. Fortunately, these flatbed scanners are pretty cheap, about $100 or less. I think we destroyed one or two in the process of coming up with this one that works. We popped the top off, cut this hole in the side, and we mounted these brackets. We actually popped this bracket to the scanning head. We've got some support bars that come up that are adjustable back and forth so we could position the tube so it sits directly over top of the scanning head. So then, as the scanner scans, it rolls the tube directly over the scanning head and it unwinds the image, so you end up with a nice image. Now, you can only get an image that's about a little over 20 centimeters long, so you got to do the two pieces and composite it together. If you want, you can chop it into segments and analyze it however you want. You can convert it into a black and white image, and you can use a cheap online image analyzer to get a very accurate measurement of the amount of paint that's been removed. And we did that for a lot of our research stuff. Most people, you don't need to do that. You're not interested in that much level of detail. So when we first started out using this in the field, we thought we could do visual assessments. Technologists are used to doing visual assessments. I used to think we did them pretty well. Where we would, we're making assessments like redox features, what percentage of redox features. We'd get charts that look something like this, and we would use those as a standard to estimate the amount of paint that's removed within a certain zone. However, when we did it, we found out that we didn't really do it. We did some testing on this. We had 16 people make these kinds of assessments, and we really didn't do a very good job. If you take the mean, these dark, this is the amount of paint removed that was measured using our image analysis technique, and this is the amount of paint that was removed that people estimated had been removed. If you take the averages of all 16 measurements for any tube, the averages are pretty good. So if you wanted to line up 16 people and have them all do the estimations and take their averages, you probably come up with a pretty good number. But most people don't have the luxury of having 16 people sitting around waiting to try to do iris estimations. So, and the average error associated with this was 9%. That was the average error from everybody on all the tubes. And however, if you look at individuals, some people can do this better than others. Some people have a good geometric part of their brain. And so the best that was done is the average is about 5%, and the worst, there's some person, name will be forever hidden, whose average error was 20%. That's the average error, 20%. So this is the range of average error, as you can see. So the best was about 5% down here, and worst, over 20% average error. And the individual errors were a lot worse than that. So what do we do? Is there a solution? This is the new solution. This is a really low-tech solution, but it's accurate. That's the good news. We can take a Mylar grid. We've got these. If you go to the Byron Jenkinson's website, we published in a paper last year. Jenkins has got on his website, you can download and print it. They'll sell you these little grids for $1, I think. Basically, there's 390 squares in here, and the grid's designed, it's on clear Mylar, so you can wrap it one time around the tube. You're holding it in place with rubber bands. Then you can take a Sharpie and just sort of mark, put a little mark in each of these squares that's got more than 50% of the paint removed from there. So you take your grid off, you count them up, how many squares, sum them up, and this is the case where we have 57, total of 390, that had 15% paint. And when we had people do this independently, we had a much better response, good replication. So the average error dropped from 9% down to 3%. And so that's pretty good reproducibility. So this is sort of what we're recommending now for kind of the average iris tube use. Now, how do we interpret the data? Once we get the data, then we've got to decide what does it mean. And I'm going to present sort of two protocols or two approaches, and one, the official approach or protocol approved by the National Technical Committee for Hydric Soils, and I'm going to present maybe something which is a little less conservative, but based on actual data that we collect. So the National Technical Committee is trying to document that a soil is reducing. The National Technical Committee says you got to look within the upper 30 centimeters, the upper foot of the soil, or the upper foot of the tube. Find 15 centimeter zone within that tube, that upper 30 centimeters where you have the maximum paint removal. It's got to be 30% paint removal. And that's what they say. So what that means is, these are 5 images, 5 replicate iris tubes. And here's the old image, so you can see that this represents where the soil surface was. And you go down 30 centimeters, so you're looking at this zone from 0 to 30 centimeters. Each of these squares, rectangles, represents the zone 15 centimeters long, 6 inches long. So you place that in each of these tubes, the zone where you've got the maximum paint removal. Right, so that's why this one's up here, this one's at the bottom. It'll, over here on these set of tubes, this one would be up near the surface. And then you determine how much paint removal have you got in each of these sections. So you can either do that by estimation, by grid, or image analysis if you're going that route. Then, if you get more than 30% paint removal, according to the technical standard, it's considered reducing. And you've got to have a majority of the tubes that show 30% removal. So you've got to have at least 3 out of 5 tubes showing that. So if, in fact, these were 3 or 5 replicate tubes, you've got 2 tubes that have got more than 15 or 30% removal, you've got 3 that have quite a bit less than that. So in this case, this would be deemed as not being reducing regard to National Technical Soil Technical Standard. Okay, I hope that's clear. Now the data that we use, this was work done a few years back by Karen Cassins and Vaughn. Dr. Vaughn is now a faculty at Cal Poly San Luis Obispo. Way back when she was working on her master's thesis, and Byron Jenkinson had just come out with the iris tubes testing it. And this graph shows along this axis the percentage of iron oxide paint removed from a 10 centimeter zone. Okay, so this is a 4-inch zone, not a 6-inch zone. It's a smaller zone. And we compared it to redox measurements, pH measurements using platinum electrodes and all that, which is also spelled out as a way to determine reducing conditions and according to the technical standards of Hydric Soils. So during a period of time, if we documented that this soil was reducing, both when it went in, when the tubes went in, and when the tubes came out, that's what this green line represents. So let me just put some data up here and see if we can demonstrate that. If we had 10% paint removed in a 10 centimeter zone that was found somewhere in the upper 30 centimeters of the soil, 80% of the time, that soil was reducing, both based on the EH measurements at the time that the tube went in and when the tube came out. We're pretty confident that that was consistently reduced. If we had 20% paint removed, then that percentage of the time that it was reduced goes up to 90%. By the time we get to 25% removal here, the soil was reducing essentially 100% of the time using the redox measurements that way. So this is a table that was this little article in Soil Survey Horizon that came out a few years ago. This is sort of my take on the paint removal. You don't see any paint removal, we're looking at a 10 centimeter section. Clearly the soil is not reducing. If you got a small amount, say 1 to 5% removal, probably the soil is not reducing with regard to the technical standard. If you're in the 5 to 10%, okay, 5 to 10% back here, somewhere between 50 and 80% likelihood. So I call that possibly reducing. These are conservative terms, I think. 50 to 80 is confident, right? If you get 10 to 25%, that's what we'll call probably reducing. That's if you got between 80 and 100%. By the time you get 25% removed, definitely reduce. So, sort of the protocol that we recommend, I think is maybe a little bit more defensible from data, is that if you have 20% removed in a 10 centimeter zone, somewhere within the upper 30 centimeters, say it's a 90% likelihood that the soil would be reducing if you made measurements. We come back to this same, and now we're looking at a zone that's 10 centimeters long rather than 15 centimeters long, so it's a little shorter. Still slide it around to find the optimal position on the tube within the upper 30 centimeters, and then count the removal there. If we do it on this one, these two are clearly, obviously, over. 19, well, error associated with this is, that's pretty close. So technically, if we want to split hairs, you might say, okay, well, this isn't quite there. 15 is also pretty high. So you have to wrestle around with this issue. I sometimes talk about with folks, it doesn't make sense to measure something with a micrometer. You're going to cut it with you're going to mark it with a wax pencil, and then cut it with a hatchet. If you don't measure it with a micrometer, if you're going to mark with a wax pencil, and turn around and cut it with a hatchet. You got to know where your sort of weak links are in the process, or sort of be consistent. So, given everything, I said this soil with 19 here is pretty close to 20, almost 20. These are way over. People need firm boundaries, and your Myers break tight. We're stuck on firm boundaries. Anyway, the next slide illustrates briefly here that the zone that you look at, using 10 centimeters rather than 15 centimeters, changes things a little bit too. This is two scans of two different tubes. Here's a tube. You take the whole 40 centimeters of the tube, and you do the amount of removal, weight loss removal on the whole 40 centimeters. You got 7.3% removal. You take removal from the zone to 15%, or rather 15 centimeter zone, we're down to 10, or up to 10%. And if we go to a shorter zone, only 10 centimeters long, it's a little bit higher. Usually, as you go from 15 to 10 centimeters, 15 centimeter zone to a 10 centimeter zone, you're going to increase the amount removed because you can be a little more specific where you focus. Over here on this particular tube, if you did the whole tube, you're at 51%. The 15 centimeter zone, you're about 93%. The 10 centimeter zone, you're up to about 96%. So you got that for what it's worth. All right, now, so that's the main way in which iris tubes are used. That's the protocol. That's the way we measure it. That's the way we interpret it. Now, in the last just couple of minutes here, I just want to give you a couple of other examples of some other things that are going on with iris tubes. Some of you may know about. Some people have suggested using manganese oxide coated tubes. Here's an example. This is from an article that was published by Cindy Stiles and Chin Ping back in Soil Survey Horizon a couple of years ago. And I think, in principle, this is a good idea. In fact, I worked around trying to do this a while back before that. And the problem is, I don't think there are any methods available to produce a durable tube coating. There's a lot of issues. I've seen some of the tubes that have been made. Just we haven't been able to figure out a way to get the manganese oxide to stick well. So you're going to have abrasion issues, scratching issues. It's hard to determine. If you're looking at these tubes, you don't see the nice sort of same splotchy pattern that you see with the iron oxide. So it's a good idea. Today has not yet quite arrived. If you all figure out a way to make the paint stick well, more power to you. Because manganese oxide reduces a little more easily than iron oxide. So it has, I think it has some real potential application. The other thing that actually does work, that we've been using, and most of you aren't going to be too interested in this, but it's for measuring sulfide in poured water. And it's based on this reaction where if you've got iron, the presence of sulfide, you can actually form this black monosulfide, it's the coating. And so it looks like this. These are iris tubes, 5 iris tubes that were put in the marsh, forget this, 5 minutes. The summer, in July or into June. But in 5 minutes, they went from being entirely orange to looking like this. That's pretty spectacular, isn't it? That fell out of my chair when you first saw that. And what we see is that the degree of blackness is a function of how much sulfide is in the water. Right? So as we increase the quantity of sulfide for the same period of time, it gets darker. This graph goes from lower concentrations of sulfide over to higher concentrations of sulfide. This also illustrates that the blackness is also a function of how long it's exposed. If you stick it in for a minute or 5 minutes or an hour or 6 hours, for a given level of sulfide, you're going to get darker colors. So we were working in some marshes a couple of summers back. There were areas that were dying back and areas that had healthy vegetation. So we put some tubes in both. These are from these tubes came out of the healthy stand. These tubes came out of the dieback area. We can quantify this. It's a fair amount of work to actually quantify. We've published a couple of papers on this. But we've shown that the sulfide levels are much lower here in the cases where the vegetation is growing healthily. Where we had dieback, we actually had a lot higher sulfide levels up closer to the surface, the upper 10 or 20 centimeters. So it does seem to work, has some environmental applications, ecological applications. We also did some engineering modifications to these iris tubes, use them in some subaqueous underwater applications. This is Danielle Baldwin, was working at some of her sites in Chickasee Bay. We could attach this to a post that we could then insert over the boat, push in, we attached floats so we could come back and find these things. And we left them in for an hour, 6 hours, 24 hours. This could not have been done before the days of GPS. Anyway, we were just doing this to show this is a soils map of Chickasee Bay, so a soils map. There's 4 different soil units. And the short version of this whole thing is that there were some pretty significant differences between soil types in terms of the amount of sulfide. Sulfide has implications for benthic organisms, for SAB, ecological applications. So anyway, we thought that was an additional application. Here are some references. These are articles that should be pretty boring reading. But if you're interested in finding more out about some of these, this is Byron's thesis. Byron and Don Transmeyer published a paper back in 2006. That's another work that we've been doing since then. And so with that, I'll stop and say thank you for your attention. And I guess I'll hand this back over to Sean and see if there's any questions that have come in.
Well, thank you, Marty. And at this time, we'll take some questions. And again, you can enter your questions in writing by using the Q&A tab at the top of your live meeting frame. And I've got a good group here at the center with me, so I don't know if there's any questions from this group for Marty while we let people write their question.
It's possible that I did such a perfect job on this, there may not be any questions. So. It's hard. One of the things I don't like about this webinar is I can't read people's body language or facial expression. So, I cracked all these sort of dry, corny jokes throughout here. I have no idea whether it created any smiles or laughter anywhere across the country. I hope some people got a little bit of enjoyment or humor out of that, but I'll just have to take it on faith.
We've got a couple questions coming in here. Okay, the first one is, where do you get tubes if you don't make your own?
Yeah, that's a good question. Right now, the only place that does them commercially is iristube.com. This is Byron Jenkinson's company. threatening to also go into business out here in the East. I got someone else that's interested in it. And it's sort of like, it's sort of how do we balance the infringement upon each other's patents? Right now, Jenkinson and Purdue own a patent on the tube, but I own a patent on the paint. I and the University of Maryland. And I did it really just to protect myself because we spent so much time developing the paint. If you use Byron's recipe, the paint won't stick. If you use our recipe, which he does, he uses our recipe, and the paint sticks. So, but if you want to buy them, last time I checked, they were like $35 a piece, which, you can pass, if you're interested in doing this as a homeowner, that's a lot of money. If you can pass that cost along to your client, then maybe it's not so bad. Now, I know they are using these in some, what am I trying to say, wetland restoration cases, in order to, as a sort of a soil standard, to demonstrate that the soils are functioning as microsoils.
Marty, a spin on that question is related. Is there a ready source of the paints for the Irish tube? So people can get their own tubes, but they don't have the paint.
No. And the paint, the recipe for the paint is published. It's there in the literature there, especially the 2006 article by myself and Steve Birch. But I know that, even the folks at Lincoln have kind of struggled some with getting paint that sticks well. You have some, you basically titrate anhydrous ferric chloride with potassium hydroxide. So you need a pH meter, you need some way to stir it, to measure the pH, you need to be able to dialyze the salts out, but maybe a centrifuge. So you really need to kind of have lab facilities to do it. You don't need really sophisticated lab facilities. You just need some basic lab facilities. But once you make the paint, once it reaches the right mineralogical composition, you can slow down the change. You can store it in the refrigerator. And once it's stored in the refrigerator, it'll keep for 2 or 3 months. You can continue to paint tubes. But of course, if you were to ship it across country and it was the summer and it got warm, the mineralogical composition changed pretty fast. So that's an issue. The paint has a limited shelf life. Now, once you paint the tubes and they're dry, they've got essentially an unlimited shelf life. So you need to find someone in your locale that can sort of make the paint if you wanted to paint them yourself.
Another paint question, did you encounter any fading of the paint, and how did you handle that?
No fading. Once it's because it's basically it's minerals. And as long as the minerals are preserved and under dry conditions, those minerals are very stable. So they're not going to be shouldn't be any changes in the color fading in the paint while they're being stored.
There's a kind of a practical use question. What about installing, reading, and then reinstalling if there was no reaction on the tube?
Yeah, I know people, especially if you buy these tubes for $35 a pop, you want to reuse them if you can, right? If they're really in pretty good shape, you could probably get by and put them back in. Normally there's some little, you get a few little micro blemishes, some little micro scratching and things like that when you put them in and out. So, even if there hasn't been any removal, they're not going to look 100% perfect, but they might still be functional. So there's nothing inherent to the tubes or the mineralogy or anything itself that would necessarily interfere with that. Now, once you've had some significant removal, I don't think you could reuse them very effectively.
And there's a kind of a short question here. I'm not sure it's very complete, but it reads, is it the same for depleted versus reduced iron?
Well, I certainly understand the difference between sort of depleted and reduction in terms of like a reduced matrix or depleted matrix in the soil. What happens with the tubes is that once the iron becomes reduced, it becomes soluble. It gets stripped away. And it's a unidirectional thing. You're not going to get the iron oxide sort of back on the tube. They're not going to reprecipitate. So I don't know whether that answers, maybe that was what they were getting at or not.
I'm not sure. Another question about the kind of tube. Would manganese coating stick to something other than a PVC tube, like a wood dowel? or is the issue the manganese coating is unstable?
It's physical. People talk about dowels, if you could sort of get it impregnated into the wood or somehow, but you're also then going to have issues in that you can get it out stripped. The PVC is good because it's inert and it's not porous. So you just have a thin little layer. If you had a thick zone, then it would be really hard to kind of see the stripping and the reduction. Wood would also be complicated because wood itself would be providing a carbon source. So that creates some additional problems.
I know that you talked about that these had a fairly long shelf life, but there's a question about that. Once the tubes are painted, what's the shelf life prior to use?
On the one hand, I would say, I don't know. But I would think it could be 100 years. Certainly years. We've got tubes sitting around for years that don't look like they change at all. So as long as they're stored dry, they're kept in kind of what's your standard, cool, dry environment. You don't want to put them in a leaky attic at really high humidity and occasionally they get wet or anything like that. I mean, even under those conditions, you wouldn't expect things to change much. Under sort of standard, dry, normal, indoor conditions, I think they'll last essentially probably for your career. Maybe two or three careers.
Okay, there's a question here from the South Texas area where they have a lot of episaturated, ponded, slowly permeable soils, alpha soils, vertisols. Any issue or special use installation considerations with those heavy textured soils?
I haven't personally installed them in those kinds of situations. We put them in fine textured soils. I think as long as they're moist and you can make a pilot hole, it shouldn't be too much of an issue. I think that would be pretty straightforward. I mean, you might only get reduction from the top, rather than getting saturation from below. If it's saturated or ponded, vernal pools or something like that, they might still be, functioning just fine. But, I don't think you really have too much to worry about, like you're going to, some people are afraid, you're going to sort of puncture a desaturated soil and drain out your vernal pool or something. I can't imagine. That's really an issue, right?
Here's a question about the alpha-alpha dipyridyl dye related for manganese. Is there a dye for reduced manganese like the dippy dye for iron?
I don't know. I don't know of it. Someone last week, I was out with the Mid-Atlantic Hydric Soils Committee, and we were in the field, and we were looking at some wet soils and used some alpha-alpha dipyridyl dye. Someone said, well, how does it work? And I said, well, the dye reacts with the ferrous iron to make this pink color. I said, well, what's the mechanism? I said, well, the ferrous iron reacts with this alpha-alpha dipyridyl dye, and you get a pink color. Yeah, but why does that really work? And I said, well, you see, it's this ferrous iron and the alpha-alpha dipyridyl dye that creates this pink color. I don't really know why the alpha-alpha dipyridyl works, but it works great. I don't know of a similar dye for manganese.
Okay. Another question about the tubes. Is the center of the tube hollow? If so, would it introduce a pathway for gas exchange?
It is hollow, and it's actually helpful to be hollow because it doesn't create, it's a way. Well, let's start with your question. I think you're going to make a pilot hole, so you're going to introduce a little bit of gas down there, but once you put the tube in there, the tube, if it's saturated, is going to fill with water. So you're not going to introduce gas introduction. I don't think is going to be a big deal. But it's incredibly helpful in terms of getting the tubes in and especially getting them out. If you just stuck a rod down there, there's a solid rod almost an inch in diameter, then extraction issues could be really problematic. We had some cases where we were using some panels. We were experimenting with painting these panels that were like 8 inches wide and feet long, and we used a wedge and a marsh to kind of cut a slot and split it in and closed it up. We went to pull the dang thing out. We had to get a winch in order to extract the thing. And so I think there's all kinds of issues. So I don't think the introduction of gas is a problem, but it's actually very helpful in terms of getting them in and out. Being a tube, it makes it strong, and they're incredibly cheap, right, because it's a sort of a standard product that's available.
And the next question is a site application question. If you have your tubes at or near the area next to the side of a hill or upland area, is it possible to get some false readings from possible iron movement from the iron-rich upland soils, basically showing that this is not reducing when it actually is? An example is where the floodplain meets the base of a hill.
Yeah, so you're talking about being kind of a discharge area. Could you be carrying ferrous iron downslope and having it precipitating on the tube? So you might be moving ferrous iron in that discharge water down at the foot slope. That's possible. I think it's pretty unlikely that you're going to actually cause that iron oxide to precipitate on the tube. Now, yeah, let me just say that. I'll stop there.
Okay. What is your recommendation on using these in coarse textured soils?
Well, they'll work for most coarse textured soils. They work pretty well. In fact, I've got a student right now working on Assateague Island National Seashore, looking at interdunal swale wetlands, Annie Rossi, and she's put in a lot of these tubes, even in those very sandy soils. So it can be done. Sometimes she gets a little abrasion. Those really terrible cases of abrasion are where we actually install, put them in the fabrication systems, and we didn't have a pilot hole. We just sharpened the ends and pushed them in. That's the worst abrasion I've ever seen. So, yeah, you might get a little abrasion in the bottom of the tubes, and you need to be aware of that. But you still try to put a pilot in, and I think they're still working.
We got time for a couple more questions. Since very hydrite reduces before goethite, wouldn't reduction on the tubes be affected by the type of iron in the soil and the level of reduction?
In theory, yes. And I think in some cases we actually see this. I think it's possible that the ferrihydrite will reduce a little more easily than the goethite. And this is why, I talk about, and I probably should have showed an example of this. I'm sorry I didn't include this, but sometimes you'll see zones on the tubes where they're really distinctly different, but they're not white. And that doesn't bother me. It's what I call substantial reduction. And what may be happening in some of those cases is that the ferrihydrite reduces, the goethite hasn't reduced. So, the whole tube is much darker orange, and then you have this sort of a pale yellow zone, or maybe some of the goethite reduced, but not all the goethite reduced. And so I don't think it has to be white in order to count it as the paint removal. I think as long as it's, contrast, let's call it sort of a distinct contrast, not a faint contrast, but a distinct contrast, and with the original paint. And you almost always, you've got some of that, especially the painted zone that goes above the ground surface that hasn't been altered or changed, so you can use that as kind of a reference. But it's true. But usually, the soils aren't sitting on the edge where you only get a little bit of reduction and not all of it. And given enough time, the goethite will be reduced too. So I don't think you have to have a white tube in order to count it as the paint remover. That's the bottom line. But it should be contrasted.
And then here's another question on kind of a special scenario. If this iris tube measures cumulative reduction, how do you justify soils that have been saturated repeatedly for hundreds of years and are totally reduced, yet in a single year they reduce less than 10% of the tube?
What you're doing with the iris tube is you're measuring active reduction. Right? The soil doesn't have to have iron in it in order for the tube to function. Okay? But you have to have microbes. You've got to have some sort of a carbon source. And presumably, if you had a saturated sand with zero carbon in it, let's say you dug out the sea horizon, put it in a bucket, saturated, put an iris tube in it, you're not going to get any reduction. You're not going to get any paint. gotta have a carbon source. So, it's a measurement of reduction. It's a measurement like alfalfa dipyridyl, although it may be better than alfalfa dipyridyl. And in some extreme cases, if you've actually reduced, and then while reduced leached the soluble iron out of the system, so you have a really depleted soil, especially if it's coarse texture. Really, there's no iron in there. You might not get much of a reaction to alfalfa dipyridyl, but you might still get removal of iron from the iris tubes. And if you have redox electrodes, you probably still measure reducing conditions. So, that gets exactly at what was being asked in the question.
Similarly, is there a minimum soil organic carbon content that you would want to utilize, or you would want to test the iris tubes in? If you knew you had a clean sand, you wouldn't bother. But is there an organic carbon content that you would recommend that should give you a positive test for reduction curves?
Well, I don't know what the answer to that is, and of course it's not just the total carbon, but sort of the more active component of the carbon. Undoubtedly, that has an impact on what's happening here. This is not entirely neat and clean. It's a field rule. Anything you're doing in the field has got certain variability built into it. I've seen cases where we put iris tubes in saturated soils. We got a lot more reduction near the surface of the soil than we did down at 40, 50 centimeters. I tend to interpret that as being you've got a lot more carbon, a lot more microbial activity up there in the surface down. So there's, it's got some limitations. If you see paint removed, those splotchy patterns, I think you can be pretty confident you had some reduction by microbial activity. In terms of minimum carbon content, certainly most upper horizons, A, EA kinds of transitions are not going to be an issue. That's what most concerned about is, they're reducing in the upper part. One of the things that I know Byron was trying to do was to try to use these for water table evaluations deeper in the soil, like we're making septic evaluations. We want to know, is there water down at 4 feet, 5 feet? I don't think these have very good application in that regard, because there isn't necessarily much of an active carbon source down deep in the soil like that. Yeah, there's a little bit. You got some roots, and you have some small amounts of soluble things down there, but I think you'd have plenty of cases down there. The reason you get depletions at depth is because the soils are old, and you get roots going down, in the same places along structural surfaces, and so you're contributing carbon sort of locally in thicker places, and you have the aggregate effect of someone mentioned another question over, decades, centuries, millennia. You can get these really depleted features going. But in terms of using these tubes in that way, I don't think I've got more reservations about that.
I've got one last question for you, Marty, and it's an easy one for you, but is wrapping in wax butcher paper an appropriate transportation method to minimize scratching and physical abrasion, or does the wax paper interfere with the iron compound?
I don't think wrapping will interfere with anything. We typically, we used to, when we were shipping them, sometimes we would wrap them up in like saran wrap, strip out, and then, just roll them up in saran wrap to give a little protection. I think that's good if you're going to transport them any significant distance, but it shouldn't have any impact on the paint.
All right. Well, with that, we'll conclude our. Oh, I have one more question from in the group. Yeah, if you would. And this is, I guess I haven't said anybody else's name, but this is Joe Scheretti. He's got a question for you.
Hey, Joe.
Hi, Marty. Marty, for years now, the standard elements indicate significant reduction in soils has been iron. So I'm just curious why you would want to experiment with a manganese-based paint on iris tubes.
Well, from a pedological standpoint, iron has always been our main key. But, from a wetland standpoint, they talk about anaerobic, right? And so anaerobic actually starts a little higher on the redox spectrum than iron reduction. Usually, in a lot of soils, most soils have about 50 times as much iron oxide as they do manganese oxide. And so they don't linger much in the manganese zone, I think, that they're becoming reducing. But also, the paper that Cindy published a couple of years ago was interesting up in Alaska, where they, you might be able to indicate reduction fast. Instead of installing tubes for like months, you might be able to get reduction in a week if you're looking at something like manganese. So it might have the potential to give you sort of a quicker look. Consultants are always looking for a quicker look, right?
Sure. So it'd be a quick screening test.
Yeah. So, but the nice thing about iris tubes is that they're actually integrating over the period that they're in. This is what I like about it. When you go out, you use alpha dipyridyl, or if you use a Redox electrode, you're taking a snapshot. It's telling you what's there today at this moment. But the iris tube really aggregates things and accumulates things over the course of a month or so. So it gives you sort of a more integrated testing. So I think that's a positive thing.
Thanks, Marty.
Sure.
And Marty, thank you so much for our webinar today. With that, we're going to close out our webinar, and I thank everyone for your time and attention. Again, this has been recorded and will be available online. Bye.
My pleasure. Bye now.